Alrighty, folks. So these notes are all about Newton's second law, which we haven't really talked about at all. We've talked about the first law, we talked about the third law. We have not talked about Newton's second law, but we actually have been using it conceptually for a while now. Okay. Before we get into those details, a quick little reminder. This deals entirely with acceleration and how the force that you apply to something can cause different objects to accelerate at different rates. And the connection there is pretty obvious when you break it down. But first, let's do a little review. Recall that when we talk about acceleration, or it's not just your change in velocity, it's your change in velocity over time. Okay, how quickly are you speeding up, slowing down, or changing directions? And a key factor about acceleration is it's a vector. Okay, now earlier we said that acceleration and your net force are always in the same direction. Okay, what we mean by that, and if I've got a little model here, okay, let's say we've got a positive and negative direction set. Okay, we've got a car, in this case our toilet car, and our cars can move either in the positive direction or the negative direction. Okay, we also know that they can speed up or slow down in either of those directions. Okay, it's not exclusive to one or the other. Now, in order to get an object to speed up in the positive direction, that means our car has to experience a force in the positive direction. Okay, so if you're moving in the positive direction, you experience a positive force. This means you're going to experience a positive acceleration. Okay, in this case, our car is going to speed up as it moves in the positive direction because they're both going in the same direction. Okay, however, our car can experience a positive acceleration, a positive force, and end up slowing down, right? If our car is going in the negative direction, but it experiences a positive acceleration or positive force, it'll slow down, right? Because these are opposing one another, okay? And the flip is also true. Let's say we're going in the positive direction. We can experience a negative force or a negative acceleration. And if this is the case, we're going to slow down. Okay, if our car is moving in the positive, but if we experience a negative force, we're going to slow down, a negative acceleration in this case. But remember, a negative acceleration doesn't always mean slowing down. And that's one of the key things that we wanted you guys to recall from our notes here. Negative acceleration does not mean you're slowing down. It only means that's the direction that your velocity is changing. So what that looks like on a practical standpoint, if our car is going in the negative direction and it experiences a force in the negative direction, okay, well, in this case, our car is actually going to speed up. Our car is experiencing a negative acceleration, but it's still speeding up. And that's because it's going in the negative direction. So this whole spiel is to remind you that the direction of your acceleration matters. We have to keep in mind which direction we're moving if we're going to make sense of speeding up or slowing down. Okay, so definitely take some time to kind of sort that out in your brain because it comes in handy much, much later, especially when we start talking about forces. Okay. And speaking of, like I said, when we talk about Newton's second law, this is all about relating forces to acceleration, okay? How quickly objects speed up or slow down based on how large the push or pull or the interaction that they experience is. Okay? So we've already talked about this too conceptually. We said that, you know, if we apply a force to a certain object for a certain amount of time, we can change its momentum, okay? So remember that an object's change in momentum, its impulse, okay, can be found if we know the starting mass and starting velocity versus the final mass and the final velocity, okay? And what we said earlier in the last unit is that if we apply a certain force over a period of time, we can change something's momentum. We can give it an impulse. And we kind of tied that back to like the Superman stopping a train situation. Remember, Superman can stop a speeding train in two ways. If he wants to bring that train to a stop, if he wants to give it an impulse, he can either apply a very large force over a very short period of time, or he can apply a very small force and he can still stop that train. It's just going to take him a lot longer to do. Excuse me. So, relaying that relationship between force, time, and impulse, we can kind of rewrite this. And what Newton actually described a force as is a force is really how quickly an object's momentum changes with respect to time. Okay, so what that means is a force is actually kind of like a rate. A force tells you how much did your motion change in a given unit of time. Okay, obviously, the larger this force is, the more we can change an object's momentum in the smaller amount of time we have. The other way you can look at this, of course, is the larger your momentum, the more force is required to stop it. Okay, but if we take this relationship between force, impulse, or change in momentum, and time, we can factor out the mass from this formula. Okay, so we end up with like force is equal to your mass times your change in velocity over time. Well, remember your change in velocity over time is just another word for acceleration. So what we're doing is we're oversimplifying this whole relationship. And we're coming out to this tidy little thing. Okay. So what this stands for is the net force an object experiences is directly proportional to the mass of that object and its acceleration. Okay. But this can tell you a couple other things too. And this is all like pretty obvious when you start thinking about it. Okay. The larger the force, the more you can get an object to accelerate. Right? But we also know that if I apply the same identical force to like a big object and a small object, let's say I apply, I don't know, 100 newtons of force to like a pickup truck and 100 newtons of force to a kid on a tricycle. If they're both experiencing the same force, they're not going to accelerate at the same rate, and that has everything to do with their mass, right? So there is this relationship between mass and acceleration and force. So here's a couple of uh, key takeaways for that. Okay, and again, it's not really anything groundbreaking. You're probably pretty conceptually aware of this fact already, but if we're thinking about a force as an interaction, okay, if your force doubles, whatever object you're interacting with, its acceleration is going to double. If the force triples, your acceleration triples. If your force is cut in half, then your acceleration is cut in half, right? So your acceleration is going to be directly proportional to that force. However, the mass is also going to factor into that too, right? So if your mass doubles, if you're dealing with something that's twice as massive, it's going to accelerate at half the rate. If your mass triples, then acceleration is a third as much. If we cut your mass in half, your acceleration is going to double, right? So your mass and acceleration are what we say is inversely proportional to each other. Okay? And so going back here, using this formula here, your net force is equal to your mass times acceleration. You guys will complete question number 5 on the formative. We want to know what acceleration will result when a 12 Newton net force is applied to a 3 kilogram object, and then also figure out the acceleration on a 6 kilogram force. So give you guys a few minutes, and then there should be a walkthrough video when you're done with that.